Hey everybody, welcome back. We are about to start Chapter 5. And just a heads up about Chapter 5. Couple of things. This one is going to be truly different for a lot of you. And this one, honestly, may be kind of difficult for some of you and some kind of easy for others because we are going over something called stereochemistry. All right, and then under the umbrella of stereochemistry, we're studying stereoisomers. Stereoisomers are compounds that have the exact same molecular formula, the exact same arrangement of bonds and atoms in 2 dimensions, but they differ only in a 3-dimensional arrangement. So they look very, very, very similar to each other, but they have a different 3-dimensional arrangement in space. And I say this is kind of difficult for some people. I personally, when I was an undergrad student way back when, I thought this was the hardest part of organic chemistry. That's just for me, though. There are other people who took to it very, very easily. That's because I am not a natural. I'm not a natural at sort of seeing and rotating 3-dimensional images in my head. Right? It took me a lot of practice to get there, so it might take you quite a bit of practice as well. While other people can do that very, very easily. This is where I want to emphasize again the importance of how the molecular model kits that I recommended can really, really help you out. And so I strongly recommend you get those or get something that can substitute for them, like toothpicks and gumdrops, because I think they'll really help you learn how to sort of rotate these molecules around and see these relationships between them. Okay? All right, so one other thing that's going to be a little bit different about this video is very visual, so I'm going to turn my camera on at certain points and sort of show you some things with the 3D models. Hopefully I won't make you too seasick by turning the camera on and off. But no, stereoisomerism is a very important thing to understand because stereoisomers, even though they look very, very similar to each other, oftentimes have very, very different properties, both chemical and physical. They can behave totally differently. We're going to take a look at a few examples along the way that are particularly interesting as we get into specific aspects of this. One example, though, and the book talks about this one, is our couple of polysaccharides, starch and cellulose. Right? You've probably talked about starch and cellulose in some biology classes. You'll definitely talk about it more once you get to biochemistry. But just to refresh you, they're both basically polymer chains of lots of units, individual units of glucose linked together. Okay? There's actually different forms of this, different types of bonds that you can make depending on where each individual glucose unit is arranged 3-dimensionally. Right? With one particular type of bond, we can get starch. That's where the glucose units are actually joined at an oxygen through an axial position. Glucose is very similar to chair conformations, 6-membered rings, so they have axial and equatorial bonds as well. So the glucose units are joined by axial bonds in starch, whereas in cellulose, they're joined by equatorial bonds, right? Everything else is the same, but this 3-dimensional change causes quite a difference in their properties, right? For one thing, we can eat starch, right? Starch is edible for us. We can digest it, right? We can break those bonds at the axial positions, but we cannot break the bonds at the equatorial positions, meaning that we cannot digest cellulose. Cellulose is commonly found, in plant stalks and stems. Wood is cellulose, right? Paper is, of course, made out of wood, so it's made out of cellulose, right? We definitely can't eat wood, I guess we could eat it, but we can't digest it. We just don't have the proper receptors and enzymes to break it down because of its stereochemical relationship. So that's pretty interesting, I think. And there's a couple of other dramatic examples, like I said, I'm going to go over a little bit later in the chapter. All right? Okay, so let's get into this a little bit more closely. We've actually already seen an example of stereochemistry. We saw it in the last chapter when we talked about cis and trans, right? You remember when we had a ring, and we said if we had a couple of different substituents, they could either be on the same side, sort of like this, or they could be on opposite sides, right? Those structures are exactly the same, except for which way the groups are pointing. So the cis and the trans, the cis and the trans versions would be stereoisomers of each other, right? So that's one type of stereoisomerism we can look at. Also, and this is going to be probably more the focus of this chapter rather than cis-trans, also we can look for something called chirality. And we can describe molecules as being chiral or achiral. All right, I'm actually going to start off with a definition of achiral. Basically what you do when you try to describe something as chiral or as achiral, you describe how that structure would interface or interact with its mirror image. It's very kind of conceptual once you think about it, but there's concrete drawings in the book and concrete examples I'll go over. Basically, you take the molecule and you pretend like it's looking in a mirror, okay? So you look at the molecule and you look at its mirror image. If the molecule is superimposable, on its mirror image, then it's referred to as achiral. And when we say superimposable, that means that you could take both the original molecule and its mirror image, and you could slide them, superimpose them, if you will, over each other and have them match up exactly. Chiral is the opposite. A chiral molecule is one that is non-superimposable on its mirror image. I'm going to abbreviate here because I'm lazy. All right. If you kind of want to, get a good idea of what chiral and achiral really mean, before we even get into molecules, you can kind of think of first of all, a pair of socks. Right. Do this. Get a pair of socks. Hold them up to each other and sort of hold them in the right and left hand, sort of like the sock is looking into a mirror, right? Then take one of the socks and try to slide it over the other, right? Is there any way you can take that sock and slide it and have it directly superimpose? The answer would be yes, right? And there's a good diagram of this in your book. I'll just refer you to your book, chapter 5. All right, the socks can perfectly match up, so they're superimposable. So we would say the socks are achiral. Now you can just simply take your hands, and I'm going to turn the camera on here, so bear with me. Oh, ignore my messy bedroom. Oh, please don't tell my wife I did that. She would kill me. All right. So. All right, so take your hand like this. All right, and then if you put your other hand in front of it like this, it's sort of like it's looking into a mirror, right? Like this. We could even, orient them differently, like this. It's still like it's sort of looking in the mirror. It's like you could draw the little dividing line down the middle of my face. The thumb is seeing its reflection over here. The index finger is seeing its reflection over here, etc., etc. All right. Now, if I just try to simply slide or superimpose one over the other, do they perfectly line up? No, they don't. Okay? Now, one thing you are allowed to do, you are allowed to physically rotate the entire molecule on an axis, sort of like this, right? Because, it's almost like you're looking at it from a different angle. So, I have to ask myself, is there any way I can rotate this hand to have it perfectly match up? Well, if I rotate it like this, and then put it on top, then, yeah, the fingers and the thumbs match up, but still, it's not perfect. Why? Because on this one, the back of my hand is facing forward, and on this one, the palm is facing forward, right? So they still, even though the fingers and thumb match up, they still don't match up overall. There is no... Oops. Yep, you're going to get motion sick watching this. Sorry about that in advance. There's literally no way to rotate my hand in any way to have them perfectly line up. So, My hands would be described as chiral, non-superimposable on the mirror image. Okay? All right. Now, those are a couple non-molecular examples. Let's see what we can look at as far as actual molecules. All right. So I'm going to start off first by erasing the screen. All right. Let's start off looking at water. Good old water. H2O. Okay, so what I'm going to do is I'm going to draw the water molecule like this. All right, and what I'm going to do, the way we represent things on paper is to basically, I like to draw a little dotted line. That sort of represents like where the mirror is, and you draw what's reflected in that mirror over on this side. All right, the H's, let's see, this H is going to be here, reflected there. The O, of course, reflected there. And this H is reflected here. Okay? So take a look at this. This one's pretty easy to see, I think. Could we superimpose these two images? Well, yeah, right? We could take, certainly, this water molecule on the left, and we don't even have to rotate it at all. We can just perfectly slide it on over to have it perfectly match up with the other one. Okay? So, let me pull up a couple of molecules here. All right, so here's water, and I've made a little molecular model of it. The orange one will pretend to be oxygen in this case. These guys, by the way, they'll come with like a legend that tells you what they're supposed to be. Honestly, I usually just make it up, so whatever. All right, and so this one's going to look in the mirror here, okay? And you can see, if I were to just take this one and slide it over, it lines up perfectly, right? So water is definitely superimposable on its mirror image, and definitely achiral. All right, easy peasy. All right, well, let's take a look at another one here. As soon as I find my stylus, there we go. All right, let's take a look at this one. We're going to look at CH2 BrCl. Okay? Now, this one's a little bit more complex than water is because we have a centralized carbon that has 4 different things attached to it. Right? It's got 2 hydrogens, it's got a Br and a Cl. Right? So what you have to do here is we have to start drawing these tetrahedral arrangements in 3 dimensions. With water, we didn't have a tetrahedral arrangement, right? We just had a bent, which is a version of tetrahedral, but the 2 atoms were in the same plane. In this case, the 4 bonded atoms are actually going to be in different planes, right? What you do, there's a couple of different ways to draw these. Here I'm showing you how to draw condensed structure. All right? So if you draw this in condensed structure, what you do is you draw the carbon with 2 bonds that are in the same plane, right? And you just represent these with straight lines. Then you draw one of them as the dash going in the back, and you draw the other one offset to it like that as a wedge coming out of the plane. Okay? And then we can put our atoms on the bonds. In this first representation, it actually does not matter where you put them. We can make it entirely arbitrary for the first one anyway. I'm just going to put the H's over here. I'll put the Br over here, and I'll put the Cl over here. Okay? Now I want to draw the reflection. I want to draw the mirror image. Well, the two H's are reflected that way. BR is going to be reflected that way. And the CL is that way. And then boom, you have your two mirror images. Now you've got to decide, are they superimposable? Are they not? Well, this one's a little harder to figure out because if you take the right structure and just drag it over and try to have the right structure lay on top of the left structure, does it perfectly superimpose? No, it doesn't, right? So if that was the only thing you did, then it wouldn't superimpose. But remember, we're allowed to physically rotate the entire molecule. So imagine this. Imagine you can just take on that right structure. Imagine you can just take your thumb and index finger, pick up the structure by that hydrogen, and sort of spin it around like a helicopter, right, or a merry-go-round or something. We could take this and we could rotate it until the BR would swing around to the front, the CL would swing around to the back, both on the right side, and then you would see that, yes, you could superimpose those two structures together, right? So this one is still an achiral molecule, all right? Now, definitely a little bit harder to conceptualize in your head. So, again, I want to show you with molecules. Hey, I got smarter this time and covered up the camera before I turned it on. Alright, so here are a couple of molecules representing the one I just put up. Okay? So what we're going to do, we'll just say that the BR is, I don't know, BR is the green and blue is the CL. All right. So if I had the mirror image, they would not look like that. There. Here would be the mirror image. Okay. I'm trying to rotate it so you can get the best viewpoints. A little hard. There we go. That's pretty good. All right. So you see how these reflect each other. If I took this one and I put it on top of there, you would see that, no, they definitely don't match up, right? But if I just take this one and spin it around a little bit, like this, we would see that now they match up perfectly. Okay? So, a good illustration of how we can use the molecular models to figure out if two structures are superimposable or not. All right. Okay. All right, now I'm going to show you another molecule. And we're going to take that same one we just did, except we're going to replace one of the hydrogens with a fluorine. Okay? So, in that case, we could have something like this. And here's our reflection. Okay? All right. So again, you do the same thing here. You try to rotate, you try to slide it over, you try to rotate it, etc., to figure out if one of the structures can superimpose on the other one, right? In this case, we can try to slide it over. Definitely doesn't work. Now the question is, can you rotate this in any manner to get a superimposable form? All right. Well, let's take a look. Okay, so here we go. Let me go ahead and get these in the right form before I do it. Okay. All right, so here we go. All I've done is I've taken the same molecules as last time, but replaced one of the hydrogens with another colored ball. I think the orangish red ones. All right. So again, just assume the green ones are like fluorine here. Assume the blue ones are chlorine. Assume the red ones are bromine. Right. So this represents the mirror images. Just like last time, if we try to directly superimpose them like that, that doesn't work. So what we can do is we can try to rotate this somehow in a manner to get it to fit. Well, I can do it this way. Well, give me a second. I can do it this way and get both of the bromines in the front, right? But that messes up the fluorine and the chlorine, right? They don't match up. Well, I can try to get the chlorine to match up, but now, trying to offset these. This is a lot more awkward than you think it is. But now, the chlorines are good, but the bromines are bad, right? You could play with this all day long and try to rotate these guys to get them to line up, but they never will, right? That's because that molecule and its mirror image are both chiral. Completely non-superimposable. All right? Very good. One thing I want to mention right now is that the terms chiral and achiral are adjectives. You describe a molecule as being chiral or achiral. We're going to run into a term a little bit later in this chapter that has a very similar definition, but it's actually a noun instead of an adjective. So just wanted to kind of make sure you guys were aware of that. All right. Another thing I want to make you guys aware of is how to draw these in skeletal form, right? I showed you how to do this in condensed form, right? You identify a central atom, like the carbon. You draw two planar bonds, and then a dash and a wedge that are kind of offset from each other, right? Skeletal works very similarly. You just sort of arrange them slightly differently. Let's say we had this guy. Whoops. All right, we have our traditional skeletal structure zigzag. All right, and let's say this carbon had a Cl and a Br on. Okay, you see really at the heart of it, it's the same as condensed, right? We have a central carbon right over here that's got 4 bonded groups. 2 of the bonds are written flat in plane. They're just not written in the same places. And then you have the Cl and the Br on dashes and wedges, right? One important thing to note, whenever you're drawing dashes and wedges on skeletal structures, the dash and the wedge always go in the same direction as the carbon, right? So, I want to redraw this because I've written all over it. Except I drew it wrong. Gosh. All right, this carbon right here is pointed up. It's on an up zigzag, so that means you point the Cl and the Br up. If you had something like this, if I had drawn it differently, the wedge and the dash would have pointed down. By the way, it doesn't make any difference on the initial structure whether you offset the wedge and the dash left to right or right to left. Like here, I could have put the dash on the left and the wedge on the right. It would have been fine. In real life, they're actually perfectly lined up. We just draw one on the left and one on the right to sort of offset them so we can see them. All right. The big thing is make sure that they're pointed either up or down in the correct direction. Okay? So if we took that original one that I had up there, which that wasn't it. Dang it. Off my game. It's also an ugly wedge, but forgive me. If we wanted to draw the mirror image of this, all right, always remember to match up your zigzags in a reflective manner. A lot of people will do this incorrectly. Remember, this carbon is being reflected right here. So make sure your frame is correct. There would be the two mirror images. And by the way, you could try to see if these were chiral or achiral. Feel free to do so here. But spoiler, each one of them is chiral. Okay? Now, in all these examples, well, all of them except for water, but in the other ones, we've been looking at central carbons, right? Carbons that have four bonded groups, okay? One thing that we can look for that'll help us identify whether a molecule is chiral or not is to look for the presence of a stereogenic center. Okay? Stereogenic center. Stereogenic center is going to be an atom, and for our purposes, it's almost always carbon, but it can be other atoms. But anyway, some sort of atom that has four different, and I emphasize different, atoms or groups of atoms bonded to it. Better say groups of atoms here to be sure. Okay? They have to be different to be classified as a stereogenic center. For example, right? We could go back to this guy. I'll just draw the two-dimensional structure here. CH2BrCl. We looked at this one earlier. All right. Do we have a stereogenic center in this example? Well, the only candidate really would be this guy. All right. So we have a Cl, we have a Br, we have an H, but then we have another H, right? These two are identical. Because they're identical, that means you do not have four different bonded atoms or groups of atoms, so that carbon is not stereogenic. I hate to separate the word, but I'm running out of space. Okay. Not stereogenic. Whereas, in the other example we looked at, right? We have a Br, we have a Cl, we have an H, we have an F. Those are all different. So, this carbon is stereogenic. Okay? And again, I want to emphasize four different atoms, as they are here, or four different groups of atoms. What if we had this one? We'll do skeletal form. Go back to an example I did a minute ago. Let's see. Do we have a stereogenic center here? Well, this is going to be our candidate. This carbon has a Cl. It has a Br. Then it's got two other carbons bonded to it. But ask yourself, are the two carbons part of identical groups? They're not. This is a CH3, right? That's a methyl group. This is a CH2CH3. That's an ethyl group. Those are different. So yes, this carbon does have four different groups attached to it. So yeah, absolutely, that one is stereogenic. All right? That's probably the most useful thing that you can look for whenever you're looking at structures to get an idea of whether they're going to be chiral or not, other than just simply drawing their three-dimensional structures and trying to overlap them. Right? Look for the presence of stereogenic centers. Here's a guide. and how it relates to chirality. All right? If a molecule has 0 stereogenic centers, it is always, and I mean always, going to be achiral. Got to have a stereogenic center to be chiral. If you have 1, then it is always going to be chiral. Nice and easy, right? If you have greater than or equal to 2 stereogenic centers in a structure, this is where you're going to hate the answer because it is depends. Sometimes they are, sometimes they're not. Depends on what other groups you have within the molecule. Right? But don't worry, later in the chapter we will get to molecules that have more than 1 stereogenic center and how you can determine which ones are chiral and which ones are achiral. Okay? So there's a couple of problems in the early part of the book, early part of the chapter, where they'll give you some practice problems and you're looking for stereogenic centers and also looking for chirality. Work through those. They're good practice. If you have any questions on them, let me know. Okay? I want to highlight one other feature that you can look at as well to give an indication of whether something's chiral or not. It's a little bit trickier to identify. So personally, I like to rely more on looking for stereogenic centers, but this does work too if you know how to apply it. Right? And that's to look for a plane of symmetry through the molecule. Right? And we've discussed this before. Plane of symmetry is where you can just cut a straight line through a molecule and end up with 2 identical halves. Right? Achiral compounds have a plane of symmetry. Chiral compounds do not. Okay? So if you can identify a plane of symmetry, then that makes your life a little bit easier, right? You can recognize that it's achiral. All right? Let's look at a couple of the examples we've gone over before. Let's look at water, right? Water is pretty easy. All right, you can draw the structure of water, and I think it's pretty simple to say, yeah, this definitely has a plane of symmetry. You could chop it right through that oxygen and end up with 2 equivalent halves. So, yeah, that one's pretty simple. Now, when they start getting more complex than that, they get a little bit trickier to identify. For example, if we go back to this one, we already said this one was achiral, so that means it should contain a plane of symmetry. Well, ask yourself, is there an obvious plane of symmetry that you can draw through this compound? Probably not, all right? Or at least if you can, then you're better at looking at 3-dimensional images and rotating them in your head than I am, all right? However, I'm going to show you this with a model. Okay, here is a molecular model of this compound, right, as drawn. If I were to rotate it like this, and then let's say I had a nice little samurai sword or something, and I chopped it right down the middle right here, then yeah, you would see you could actually get a line of symmetry through that and have 2 equivalent halves. So yeah, this one, even though it doesn't look like it on paper necessarily, does have symmetry. However, we replace one of those H's with an F, right? Make it CHBrClF. You can see we can try that same little trick, chop it down there, and it doesn't work anymore, right? Because this is not a hydrogen. So this way, for this one, there's no way that you can chop it in half and have a plane of symmetry, and that corresponds to its state as a chiral molecule. Excuse me. All right, so as you can see, Actually, one more thing. I was about to end it, and then there's one more thing I forgot that was in my notes. So let me go over it real quick. Okay. All right. So we said that whenever you're trying to determine chirality and superimposability of all that you're allowed to take the entire molecule and sort of rotate it around. All right. Also, when you're doing this in larger molecules, you're also allowed to rotate around single bonds. Because, hey, that happens in real life, right? You're constantly rotating around single bonds. So that's sort of another little thing to check for. Here's an example. This one, when you first look at it, and this one has 2 stereogenic centers. Now, whenever you look at this one at first, this one doesn't really look like it would have a plane of symmetry, right? You could try to cut it in half like, maybe here. Whoops. I didn't mean to put a Cl there. Gosh, that would complicate things. That's a CH3. My bad. All right, this one might look, like you can't really draw a plane of symmetry, right? Because you chop it between those 2 carbons and everything looks like it's pointed in the wrong direction. However, you are allowed to rotate around that single bond like a helicopter, and you'll see that the same molecule can have this state as well. All right, so if we rotated that right side, right, you could rotate it about 180 degrees, and that CH3 that was pointed on bottom would then point up there. Your wedge and dash would go to the bottom and switch places. So now your H would be on a wedge going forward, and your Br would be on a dash in the back. And now, lo and behold, yeah, you can see that we can easily draw a plane of symmetry there. So this is an achiral molecule, even though it has 2 stereogenic centers. Okay? So those are the things you're allowed to do whenever you're rotating, spinning molecules and trying to figure out if they're superimposable or have planes of symmetry. You are not allowed to break and rearrange bonds. That is the limitation. All right? I'm going to end this video here. There's a lot more to go over in this chapter. It's fairly lengthy. And as you can see, it's definitely a bit more complicated than some of the other topics we've gone over. So be sure to stay on it and really go ahead and get some good work in on this. And if you have any questions, let me know. Until next time, talk to you later.